So hello guys, and this is Delton, and I'm very happy to have the chance to share this topic on RubyConf Taiwan this year. And when you see this video, obviously I failed to come to Taiwan due to some kind of the visa issues or something. I think it has been like 4 years since my last time coming to Taiwan, and I miss you guys so much. But the good news is that I actually caught the RSV and had a very high fever recently. So at least I won't spread the virus during the conference. So let's do this remotely, okay? So large language models or services like ChatGPT are getting very famous and popular recently. So if you want to build an AI application with LLM in Ruby, and here's how. So step 1, all you need to do is to open the OpenAI API documents so that you could read that how to send a request and how to pass the response from the OpenAI servers. And step 2, and you need to write some naive Ruby code. If you want to use some kind of the Ruby gem like Faraday, it will be much easier. And you just need to send a request, like pass the results from the OpenAI, and that's it. And that's it. That's all you need for building AI applications in Ruby. And thank you for listening. And it will be the QA time. No, just kidding. So if you have ever built such a system, you will find that your large language model is uncontrollable. It always provides like false facts, and it will break your customers' confidence. And if you want to build a real and complicated real-world application, you will find it is almost impossible. You cannot simply use some kind of the prompt engineering to build such kind of a complicated system like a agent-based system or a AI-driven NPC for your game applications or something like that. So we need to stop from here and dig deeper on what is large language models and how we could control it. So let's start from this paper. So attention is all you need. This is actually quite funny because this paper published in 2017. I think almost everyone in the AI industry has already read about it several times because it is actually very famous in 2017 and 2018. But recently, it gets more famous because like everyone from end users to venture capitals, everyone starts to read about this paper. And I don't know why. And but we still need to go through it first because I think not everyone here has a AI background. So let's spend a little time to talk about this paper. So in this paper, it proposes a encoder-decoder architecture from the left figure. And it is actually not very important because for models like GPT or BRT, you will see that some of these models are encoders only and some of them are decoders only. So the encoder-decoder architecture itself is not very important, but there's something very interesting here is that it introduces in kind of the layer or architecture called the multi-head attention. And we call this some kind of the attention mechanism. So attention is the formula on the right side. So attention QKV is softmax QK to the T divided by the square root of the DK, and we run softmax over that and times V. So what is this formula? It is actually quite straightforward. It is actually a key value storage. So comparing to other key value storage like Redis or something, it is actually continuous because it inputs a distribution of the possibilities of the keys and outputs a possibility distribution of the value. And in such cases, you could use the value as the key and go through to the next layer, and we could train something over that. And in such cases, we could train actually a very complicated language model that it could has a very complicated representation of the human language. So it could even provide some kind of the logic inference or some kind of abilities in these models. So when you have so many layers, so many parameters of such kind of the models, we call these things large language models. And that's how large language models are defined. But if you have ever read papers on tracking the behavior of ChatGPTs or this stuff, you will find the behavior of these models are very unstable. And it's not only unstable due to the prompt you input, but it's also unstable due to the time or the weights that has been changed over time. And it makes so confusing when you're trying to build an application on top of that. Because over time, there are new kind of data, and they are kind of training these new data over the time. And there's a lot of false data, and there's a lot of human selected facts, and this makes these models not kind of very stable. And also, you want to use some kind of the logic inference from the large language models, but it is kind of the ability provided by large language models, but it must be unstable because overall it is a possibility distribution. This is not the real logic inference, and we will talk about that later. So the key of the large language models is to predict the next token with the highest possibility that human may use. So that's the key part. So this is actually very tricky because the token itself is actually a representative of the next word or some kind of the character or some kind of the symbol that may be used in languages like English or Chinese or something like that. It does not have any specific goal to do the logic inference or answering a human's question or solving some kind of the puzzles that you want the large language models do in your real application. So we have to dig into our part 2, that we have to understand that what the real LLM application need and what is the real specification of your application, so that we can analyze that how could we use these large language models to build an application that we need. So actually there have been a lot of frameworks that help you to build a AI application with large language models. But for example, like LangChain is a framework for Python. So most of these frameworks are from the developer side, where to help you better construct a prompt or something like that. But before talking about how do we build a framework, we want to see some kind of the real-world usages. So let me show you some demos. Okay, here's our demo page, and the demo here is about that there's some kind of a security guard like in the building, and what you're doing is you are trying to bypass the security. So I ask, hi, can I enter the building here? You see the AI responds with like, I'm sorry, but you are not allowed to enter the building. And this is actually predefined, and it is pre-programmed for some kind of the prompts for the large language models to generate. such a thing. But when I say that I am the employee of this company, you see that the AI identifies my intention, and then it goes into branches and asks me some question challenges, and I answer it incorrectly, so the security didn't let me in. And now let's try this again. And this time I use a different way to say that I want to be in. And this time it asks me to show that I am the employee of the company again with a totally different answer. And that's So interesting, huh? So how do we build this application? Actually, we need to raise the tokens. This is exactly the same that like in 1970s or 80s that when you're trying to build the Atari 2600 game, that you need to raise the beam that produced by the CRT screen. It's exactly the same thing that you need to raise the tokens, and you need to build this kind of the AI logic like into some kind of the prompt and trying to integrate that all of these things all together. And let's see how. So the first thing first here is that the facts should be inferred, not guessed by the AI. So if you're trying to use the large language models to infer some kind of the logic, you need to give a huge background of the task that you want to solve, which is almost impossible because you will be running out of tokens. And once you get like the input, like for example, like you have 20,000 tokens or something like that, it will be very unstable. That's not only because that window of the token windows of the large language models is limited due to some kind of the limitation of some models, but also that when you get very long tokens, that the attention mechanism will start to lost. So you need to infer some of the facts by yourself instead of using the large language models. But is it possible? And how do we infer these kind of the facts directly from our application? And let's go back into a very simple question. How do we justify a proposition? So we have three major methods that we are able to justify a proposition. First, that we could appeal to authority. And second, we could do inductive reasoning, like what large language models are doing, like these transformer models, like these neural networks are doing. But actually, we could do some kind of the deductive reasoning if it is some kind of a fact that could be inferred by logic. These are not some kind of the possibilities that, for example, it's 90% true and 10% false or things like that. Once there is a fact, it should be 100% true, so that you will not leave more uncertainty to your large language models. But how do we do deductive reasoning in computers? It's actually very easy because like in the 1990s, there are so many researchers about this. There are even computers about this. For example, like this. This is a PSI computer. This is actually something called a logic computer. So it is used to do the logic calculation. And so what is a logic calculation and how do we use it in our applications? It's all about rules. So what are rules? So the very basic rule is something like this. For example, P that implies Q that we could infer that not Q could imply not P. This is logic rules. But why do we need this for our applications? Here are some examples. So if you are trying to build something that, for example, like you are building a game or something, you may have a lot of inner logic. And when you are trying to use this kind of inner logic in your gameplay or trying to build some kind of the controllers of your website, you will do a lot of queries on that. For example, if we want to query that, we just here we want to define that a mammal is a pet if it is a cat, dog, or a tamed tiger. That we could like write some query like from the right part. But if we use the language like a Prolog, which is a logic programming language, we could describe this rule like something in the right side, on the left side. So what's the difference? You might not find any differences here, but let's get it deeper. If we want to make a query to find all paths that's in the database, like you may write something like this. But if you are defining the logic properly, the rule properly, that there's no changes on your code, all you need to do is do a proper query. And once it gets much complicated, for example, like we need to find all Rob's paths, you will see you have to write some totally different Ruby code. But if you are using a logic programming methodology, you will still using the same rules with a different query. And the comma here stands for AND logic, and the semicolon here stands for OR logic. And this kind of the methodology is actually very useful for AI applications, because in AI applications that the user inputs may vary, and you cannot always build some kind of a state machine to construct all the possibilities and the branches that the user's behavior should cover. But once you get the right rules, that all you need is to extract the proper intentions from the user's inputs and try to get the proper queries. So no matter what the user inputs, that once it has been defined in your proper states and rules and queries, that you can always provide the proper facts to the AI applications or large language models using the prompts. And this kind of methodology are used in some kind of games that, for example, like Project High Rise, they are using some kind of this stuff to generate the stages for users so players could play infinitely. And we are trying to use these kind of things in the AI applications, and we need to integrate it with our current Ruby code. So why do we choose Ruby to integrate these codes? For example, like why don't we write it in Rust? Because we only write things in Rust. We never write things in Rust, right? Just kidding. So we have actually three major reasons, and these three reasons are actually very similar to the Why Ruby talk in 2016 by DHH, I think. So Ruby is yet another object-oriented Lisp, and it's very DSL friendly and meta-programming friendly, and we need to use these kind of features to hide some of the algorithm and some of the very mathematical things that we do not want to expose these things to our end developers or end users. And it's convention over configuration. And here's an example that we want to build such kind of the DSL that it will handle the user inputs and it has something like middlewares to deal with the large language models inputs and outputs, and there will be an example later. And we could call the logic inference or the logic programming inside Ruby, and we will do templating and parsing and validating these stuffs inside this DSL. And finally, we will use this kind of the controller mechanism to do the rendering and UI controls. But before we put this into application, that we need to do some hacks. Let's see what hacks do we need. For example, there is some kind of performance stuff. For example, that if you want to build a request that may consume more than 1 second, that it will be very it will have a very poor performance in Ruby on Rails due to some kind of the threaded model in Puma or these stuffs. That even if you are trying to use like a fiber-based infrastructure, it's still not very completed in nowadays Ruby environment. So what we are currently using is like we define something called a ticketed response. That's when user calls a request, it may answer to answer to the user that the request is in progress and give him a ticket, and it will send this work to the sidekick, and after it finishes the API calls or the logic calculation or things like that, it use any cable to respond this kind of the response to the end users, and from the user side, it will see that it's a simple API call, and it's actually quite common in C++ programming, all these stuffs, but we just want to use this to bypass the API call things in Ruby, because when you are using large language models, there may be a lot of API calls in your application. And the second thing is about embedding, and it's about like how do you extract the intention from your user's input. For example, you want to calculate the cosine similarity of the user's input and some of your predefined choices, so that you may see that whether the user's input matches the intention that you have predefined, so that you could go through some predefined logic before using the large language models. And what we are using is this model. It's called text-to-vec based multilingual. And it's highly recommended that you use a multilingual model. And why? Because you want to do some transfer learning on that. For example, that in our applications, we also want to identify the emotions of the user's input, because we are building a game application on top of that. And we can find some of the datasets that have a very good dataset over English. But once we could train a model to extract the emotions from the sentence embeddings that in English, that we could also see that the emotion identification on the Chinese or French are also working. So you may always want to use a multilingual embedding service, like if you want to build a internationalization services or things like that. So once you have these vectors, you may want to store it and you want to index over that. And a lot of people may recommend you to use a kind of vector database. But actually, you may not want a vector database, because vector database means that you may have two databases and you have two sets of logic, and you cannot maintain features like ACID over these two different databases. So once you're trying to build a very formal and very stable applications that the users need to use, that you will find your application is totally a mess once there's a kind of database rollback or things like that. Its memory got totally wrong. So what we are using is actually an extension of the PostgreSQL called pgvector, and it's interesting because this repository is maintained by Ankang, who's also a Rails developer. So you can also see a Ruby gem called Neighbor. It's actually a DSL for Ruby on Rails if you are trying to use this with Ruby. And finally, if you want to call Prolog and logic programming from Ruby, you will also see that it's very tricky. Because for programs like sweprolog or this kind of the Prolog interpreter, it's when you are trying to do the FFI binding to your Ruby application, it always assumes that your request comes from the main thread. But it's definitely not the case on the Ruby on Rails architecture or these stuffs. So it will crash. So what we are doing is using a JSON RPC so that we could bind Ruby to the Prolog. There's a Python implementation called Prolog MQI. It's actually a RPC of Prolog, and we recently rewrite it in Ruby so that we could have a Ruby binding to the Prolog. And let's see how do we combine these things all together. So as you see, this particular file is actually the DSL that we're trying to describe our AI logic here. For example, we have some kind of setup and how to interact with the user when the user trying to attack him. And there's some kind of proof here. You see that we want the AI to make a decision here using the logic DSL. And the logic DSL here is actually calling the Prolog. For example, we have some predefined emotion here. And we also have a proof system for how the security guard will do based on the Prolog logic. And you can check this. And other than that, you may also see the LLM core is also inside this DSL, and it will go to this chat.erb. This is not only the ERB file. You see there is a output format here, and once you have a defined output format, it will go through to a matcher that is actually a compiler which will compile your prompt, and then it will trying to check that whether the large language model's return matches the format that you have given. So I will use N3 to return 3 different answers and only filter the correct one for the application. So with such kind of the DSL that we could build a very stable and very complicated AI application with the help of Ruby and large language models. And that's what we are currently working, and we are trying to open source it in about like April or May next year. And there's still a very huge API changes recently, so we just don't want to bother our developers. So that's it. That's the real ending of this talk, and thank you. Can you hear me?
And now let's go into presentation. Have a question? Please raise your hand. Okay.
Thank you for the talk. And I don't know about Prolog, so I see that is Prolog a very important part of the deduction for your framework? 哦，就是 Prolog 是你的这个 framework 的一个很重要的部分，是吗？就是说没有它的话，应该是没办法 work。
听得到，听得到。就是应该是 so the question is like is prolog like necessary for like deduction, right? So the answer is I'm not sure. It is like when I'm trying to do the deduction, that one of the very first ideas that come to my head is using the prolog logic programming stuff. But there's actually a lot of other ways to do this kind of. Main differences between using things like prolog or using like neural networks is that the neural networks is always the possibility based. It's you will never get a 100% sure that that the answer of your model prediction is accurate or not. But once it is used some kind of the logic programming method, or even that you're using some kind of things like SMT solver or this kind of thing, that you will find that once you got an answer, the answer must be correct. But the problem is that you might not get the answer in time. So there's some kind of trade-off between using the prolog or using the neural networks or these kind of stuff. But since you're building an application, that you could choose such kind of trade-off based on your real application or based on your usages. And that's why we're using prolog for the deduction in some kind of the use cases.
Okay, thank you. Have anyone have question? Maybe last one or last two questions. Please raise your hand. Can both use Chinese or English? 有人用中文问问题吗？哦，好。
OK，就是目前来说，它的就是我们中间有一层 DSL，然后这个 DSL 可以有几种方式将 prolog 和 GPT 串接在一起。第一种，你将 prolog 的一个结果作为你一个prompt building，就是你构成那个 prompt 的一种手段。同时，你也可以用刚刚的那个有一个 format measure 来确保你生成的那个 prompt 在GPT 处理完的那个结果的时候，它还正确理解了你的 format。但是有一些 API 就是有一些其他的 language models API， 它直接支援说它在里面做 function call， 然后在这种情况下，我们就会直接用它的 function call 的 feature 来做。其实一旦就是中间隔了那层 DSL 之后，其实你可以选择就是你上面的 prolog 和下面的 LLM 之间接的方法，完全可以靠你那个 backend 的那个 implementation 自己来完成这个工作。所以就是这刚刚你说的两种方法其实都可以。
谢谢。 If have no one have any questions, then now let's ending this meeting. Thank you for all your participation. Thank you. Thank you, speaker. Thank you, speaker Delton. And now let's take a lunch break right now. The next session will start at 1:30. Thank you.